Section: Introduction. In this section, we discuss the increasing need for converting traditional production records in biomanufacturing into structured digital formats to meet compliance and analysis requirements. The industry has long relied on paper documentation, and even small steps towards electronic records are significant for digital transformation. A crucial aspect of this transition is schema adherence, meaning that AI systems, like large language models, LLMs, must produce data that fits a specific format exactly. Any errors, such as missing information or incorrect formatting, can compromise data integrity and compliance. This presents a challenge because while LLMs excel at generating free-form text, ensuring they produce structured outputs that meet schema requirements is complex. LLMs generate text based on probabilities, which does not guarantee adherence to a specific format. Studies show that even advanced models can struggle with format consistency, with success rates for producing correct structured outputs varying widely. In regulated biomanufacturing, even minor formatting errors can lead to compliance issues or necessitate costly corrections. Developers often invest significant effort in adjusting prompts and processing outputs to achieve the desired format. Unreliable formatting can erode user trust, making it essential for outputs to be both credible and useful. We also explore various strategies researchers are using to ensure LLM outputs adhere to schemas. One approach is supervised fine-tuning, where we train LLMs on specific data to learn the required output structure. While this can improve accuracy, it is resource-intensive and may limit the model's flexibility outside the training data. Another method is reinforcement learning with human feedback, which helps refine model outputs based on human evaluations. Additionally, constraint-based decoding integrates schema rules directly into the generation process, ensuring compliance by only allowing outputs that fit the schema. This method guarantees adherence but can introduce complexity and slight delays. Prompt engineering is a more accessible technique where we craft input prompts to guide the model towards the desired structure. While this method requires no retraining, it demands significant manual effort and may not always yield consistent results. We also consider hybrid approaches that combine constraint-based decoding with prompt engineering, enhancing schema adherence by embedding schema knowledge into the prompts and using specialized procedures to maintain structure. Each of these methods has its trade-offs, particularly in regulated industries where accuracy and compliance are critical. We emphasize the importance of ensuring that LLM-generated records are both content accurate and format precise to meet quality and regulatory standards. Ongoing research is needed to develop robust methods for aligning LLM outputs with predefined schemas. Section Summary. In this section, we discuss the challenges of converting legacy biomanufacturing records into structured digital formats, emphasizing the need for AI systems, particularly large language models, LLMs, to produce schema-compliant outputs to ensure regulatory compliance. We explore various approaches to achieve this, including supervised fine-tuning, constraint-based decoding, and prompt engineering, each with its own trade-offs in terms of complexity, cost, and reliability. Section: Method. In this section, we describe a reasoning-driven approach that utilizes synthetic data creation and iterative reasoning with large language models, LLMs, to ensure adherence to schemas with minimal effort. We will show how to build a reasoning dataset, create both unstructured and structured synthetic data using controlled prompts and the Qwen 14b, 32b models, and reverse engineer how unstructured text fits into an empty JSON schema by using a distilled version of DeepSeek R1 Qwen 32b. This process involves explaining step-by-step how each schema field is filled. We will train our reasoning model using reinforcement learning, RL, and supervised fine-tuning, SFT. We will develop custom reward mechanisms that assess how well the outputs match a predefined schema while also considering fluency, completeness, and correctness. We will train the R10 reasoning model based on the Qwen 2.51.5b model using RL and a dataset of synthetic unstructured and structured pairs, integrating custom rewards into the GRPO framework without changing the core optimization process. This combined reward will guide the training to ensure the model produces high-quality outputs. For our reasoning dataset, we will use the distilled DeepSeek R1 Qwen 32B model with a prompt that instructs the LLM to provide its reasoning process, detailing how text maps to the schema. This self-explanatory approach helps maintain schema fidelity and clarifies the logic behind each decision. By varying the domain and text formats, we create a dataset that enhances the LLM's resilience to different formatting styles. Once we have our reasoning dataset ready, we will train a small foundation model using GRPO, following a minimalistic approach similar to DeepSeek R10. We will use a 1.5B parameter base model to develop reasoning skills without supervised data, focusing on self-evolution through pure reinforcement learning. By employing group-based advantage calculations and well-designed reward signals, we will instill structured reasoning capabilities efficiently within a resource-limited setup. We will incorporate multiple reward functions to encourage both format and content correctness, ensuring the model produces outputs that excel in all relevant areas. This entire process will remain computationally efficient, demonstrating that strict schema adherence is achievable even with smaller models. Our JSON-based reward algorithm will balance schema accuracy through key-value matching and structural completeness by comparing the length of the predicted JSON to the actual one. A high reward indicates that the predicted JSON closely aligns with the ground truth in both content and size. We will also implement a format verification reward that checks for the correct use of specialized tags, which is essential for tasks that depend on clearly defined reasoning and final answers. This binary reward simplifies reinforcement signals, focusing on structural correctness rather than content accuracy. An optional logging step will allow us to sample a small portion of outputs for qualitative review, aiding in diagnostics and future training data refinement. While reinforcement learning enhances reasoning capabilities, supervised fine-tuning provides the necessary final adjustments to ensure outputs are logically sound and aligned with real-world standards. RL optimizes for general correctness but may miss specific nuances, while SFT exposes the model to explicit examples that clarify how to handle edge cases. By adding a final SFT stage, we will ensure that our model meets strict output requirements, producing results suitable for compliance and auditing. For SFT, we will use the Unsloth training framework on an A100 GPU, completing the process in about 3 hours. Section Summary. In this section, we present a reasoning-driven methodology that utilizes synthetic data and iterative reasoning to ensure schema adherence in structured outputs while minimizing overhead. We detail the creation of a reasoning dataset, the training of a small foundation model using reinforcement learning and supervised fine-tuning, and the implementation of custom reward mechanisms to enhance schema compliance and output quality. Section Evaluation. In this section, we evaluated 5 models: Think JSON, Original DeepSeek R1, Distilled DeepSeek R1, QWEN 1.5B and Qwen 7B, and Gemini 2.0 Flash, focusing on their ability to extract structured data from a benchmark of 6,500 rows. Each row was analyzed to either create or skip a valid JSON object. We measured several metrics, including the number of rows with no output, the number of rows producing valid JSON, the average percentage of correctly matched fields, and the average percentage of unnecessary or incorrect tokens in the JSON. Our results showed that Think JSON performed the best, achieving a mean match of 62.41% and the lowest noise at 0.27%, indicating it produced very little extraneous output. The original DeepSeek R1 also had a good valid JSON coverage but had a lower mean match of 41.43% and higher noise at 11.14%. The distilled versions, QWEN 1.5B and Qwen 7B, performed poorly overall, with many rows lacking extracted JSON or containing excessive noise. Gemini 2.0 Flash had a moderate mean match of 42.88% but also faced significant noise at 10.86%. These results highlight the effectiveness of our structured reasoning approach in generating clear and valid outputs.